Okay, so today I want to talk about four more type classes. So we're going to start picking up the pace on the type classes a little bit. We talked about semigroup and monoid last time. I'm going to extend those, or talk about a set of related type classes, and then I'm also going to look at monad again and talk about a set of extensions to monad that build on the extensions of semigroup and monoid. But let's start with our monad example that we looked at a while back. So here's our definition of monad. I don't think we looked at this example. When we looked at monads, we were actually deriving it ourselves. So this is the definition of monad in the structures library. We're not actually seeing like flat map and pure here, which remember those were the two primary functions in monad were flat map and pure. Rather, we're getting each of those functions from these two base types, flat map and applicative. But those are both abstract. Flat map and pure are both abstract in this trait, and everything else is concrete. You can see here the only thing that's actually in this trait is an overridden version of map that's written in terms of pure and flat map. And so we're not going to look at the flat map type today. That's the new thing here that defines the flat map method. But nonetheless, we'll look at it very briefly just to see. It does define flat map as the one and only abstract operation. But we're not going to talk about what flat map is today. That's a topic for a few weeks from now. Okay, so when we looked at monads, we talked about at least at the end in the Q&A section, we talked about the ability to filter elements out of a monad. And you might recall we tried to write it. So let's do that again here. And so let's try to write it. We'll say that given an f of a value, and given a function from a to Boolean, we want to return an f of a value. So obviously, like if we had like a list, filtering on a list would remove all the elements that returned false. If we took the option type constructor, filtering an option would turn a sum into a none, but would leave a none as a none. And so when we tried to write this, we got in a bit of a pickle, right? All we have to work with is flat map and pure. We have this function f that requires this type a, and we have an f of a. So one option is like we could flat map it. And apply our function. This is what we did last time, but we have a bit of a problem here. If our function returns true, we want to return fa as our value. If it returns false, we need like this notion of an empty, right? So whatever this empty thing is, we need it to represent like an f of a. It has to be of type f of a that has had this value removed from it. So for like for the option type constructor, empty would be none, and for list, empty would be the empty list. And so we're stuck here because we don't have that capability of adding this empty, right? So the suggestion that was made when we had our talk on monads was, well, can't we just ask for a monoid in order to be able to do this? If we had a monoid of a certain type here, then maybe here we could just say like m dot empty. Let's check our monoid type. Yes. Okay, so if we could say m dot empty. Now, we're calling flat map on an f of a, so we know that this function has to return an f of a. Or of course you could return an f of b, but since we're trying to get to an f of a in the end, we know that this function has to return, or this expression has to return an f of a. We put f of a, the value fa on the true side of the condition. So we really just want this false side of the condition to also be an fa. And if we look at monoid, whatever type we stick in for the type parameter, that's what we get back from empty. So a monoid of a gives us an a. If we had a monoid of f of a, we'd get an f of a. So really what we want here is this monoid of fa. And we could make this work. Like this should compile, unless I did something silly. And so syntactically, this function makes sense. The problem with this definition is that there's nothing that ties this monoid to flat map in any way. So it might be a useful function when working directly with certain data types, directly with certain type constructors. Pretending for a moment that our collections, pretend that they don't have things like filter defined on them. Then if we are working directly with a list or directly with an option, this filter method would give us the ability to filter things out, given that we can define a monoid for those entries. And that's kind of an interesting fact in and of itself, right? You can filter things out as long as the type constructor is a monad and the proper type, when applied with your A type, is a monoid. So it's an interesting fact, but it ends up not really being useful in a deeper sense, right? Because while it's a useful function when you know what f is, when you consider like a parametric version of code where all you know is you've got like a monad, some monad f, chances are you don't just want some random monoid fa. You're looking for some very specific behavior. And we're going to talk about that behavior. We want to describe the relationship between like the monoids empty and flat map, how they interact with each other. And we're going to do that via a type class, and that type class is going to have a set of laws associated with it. So in summary of this intro, this filter method, while certainly legal and certainly useful when you know what f is, ends up being a little bit too ad hoc, a little bit too Wild West. To really be useful in any deeper sense. So we're not going to define this filter method, and instead we're going to look at a set of type classes that let us define a filter method with a deeper meaning. In order to do that, we're going to start with some basics. So let's go back to semigroup. Remember, semigroup was just an abstract operation defined on some type A that can combine two values of type A into a new value of type A. And the only law for combine was that it was associative, right? We can combine x and y and then combine the results of that with z. And if we do that, we must get the same results as combining x with the results of y and z. Let's take a careful look, though, at the type parameter here. Semigroup is defined on one proper type A. And our combined method does not take any type parameters, right? Our combined method itself does not define type parameters. It uses type parameter A, but it's getting that type parameter A from the trait. So what I want to introduce now is a generalization of semigroup. There's lots of different names for this type class. We're going to call it Semigroup K. And the K stands for higher kinded. So while a semigroup is defined for a proper type, we're going to define a semigroup K for a type constructor of one argument. And then we're going to define a combine operation. The combine is going to look exactly like our semigroup combine, except that we're going to define it taking a type parameter A, so that when we do the combination, we can say combining an f of A with another f of A gives us an f of A. So in some sense, this is a much stricter definition or a much stricter type class. There's many less types that you can write lawful semigroup K instances for than you can write semigroups for. There's no interesting semigroup K instance for integers, right? Because integers are not type constructors. Integers are types, or proper types. But there are type constructors that we can write the semigroup K for. We'll look at a few in a second. The other interesting way to look at semigroup K is that it describes type constructors that can generate a semigroup f of A for any type A, for all types A, right? It doesn't matter what you stick inside, you still have a semigroup, or you can generate a semigroup for it. You can synthesize a semigroup. Right, so this toSemigroup method here defines that. We say that we're going to be defined universally. We're universally quantified, right? Any old type in the world you can put here, and we can give you a lawful semigroup for f of A because we've got this lawful combine method up here. And you can see it's implemented really simply, right? This is just syntax in a sense, where all we've done is sort of like a type parameter pushdown, if you're familiar with, like, Martin Fowler's refactorings. We took the, in semigroup K, we have a type constructor here and a type parameter here, and all we did down here was pushed that f type constructor down into the main parameters of the semigroup type. Okay, so all semigroup K instances can yield an infinite number of semigroup instances, right? For each semigroup K, you can have an infinite number of semigroups because it's defined universally over all types. The inverse is not true, right? Given just a semigroup, you cannot derive a semigroup K out of it. At least not one that's sort of interesting. There's a bit of a type theory trick where we can kind of create an uninteresting one, but for all intents and purposes, you cannot generate a semigroup out of a semigroup K out of a semigroup. So let's think of an instance for this. We've already talked about two. We have list and we have option. Both list and option we can define semigroup Ks for. So let's do it at a REPL. So down here at the REPL, whoops. All right, down here at the REPL, let's just say like list semigroup K. Equals new semigroup K. Right, and so as we're writing this type signature out, think of parametricity from last week, right? We're defining the list instance for semigroup K, so now we can use information about lists to implement combine, but we have no information about A, right? All we know about A is that it's a type. We don't know anything about it. We're not allowed to use equals. We're not allowed to use toString. We're not allowed to use hash code. So there's nothing at all we can possibly do with this A parameter that takes advantage of any knowledge. Okay, and the obvious implementation, or the most direct implementation of combine, would just be concatenation, just like we did with this semigroup, like the kind 0 semigroup, the regular semigroup. Think about how we would write the regular list semigroup, not semigroup K. Well, we're in a bit of a pickle already because semigroup has to take proper types. And we can't just put list here because list is a type constructor. So we need to be able to put list of A. If we were able to write that as list of A, then certainly we could just take, we could implement combine in the same way we did above. With the one difference being that we don't have a type parameter to combine. The problem here, of course, is that we're trying to put a type parameter A into this definition, but A is not bound to a name here. It's not an actual parameter. So we would have to define it over here as a type parameter A. But now we can't have a val. We have to change this to a def. So it's kind of interesting that our higher kinded semigroup list SGK could give us the proper semigroup for any specific type via our two semigroup method. And you can see this relationship too if you look at this def. In the def, we're saying that we can generate a semigroup for lists for all A, and we're not putting any constraints at all in this A type here. So using our parametric-based reasoning that we talked about last week, we can argue that whatever comes to the right of this equal sign knows nothing at all about A, and therefore the actual type here plays no role in the behavior of this semigroup. Okay. Let's look at option. Let's try to write the one for option. So we're going to say opt SGK. All right, so here's the method we're going to have to fill in. And I forgot a type parameter to combine. So 1 second. Okay, there's the signature we have to fill in. Now we don't have like an option concat, of course, right? We can't just concatenate two options together. So let's think about what we do know. We know that X could be either some or none. We know that Y could be either some or none. Our first three cases that we typically look at, we can pretty much use as is. So if you recall, well, I don't have it split out here, but if you recall, when we derived the semigroup for option, basically what we did is said if they're both none, return none. If the left is none and the right some, return the right. Vice versa, right? If the left value is some and the right value is none, then return the left value. And then recall our last case when they were both some was the only kind of interesting case where what we did is that we used a semigroup for A to combine the two values together. And actually, let's go back to that definition here. You can see that it's not doing pattern matching; it's just doing nested folds. But basically, it's saying XX is the case, gives us the A value when X is some. YY gives us the Y value when Y is some. And you can see in the case where both of them were defined, we combine the X's, X and YY with the semigroup for A. Well, we can't implement this. We can't implement semigroup K for option using this algorithm. Because here we have this dependency on a semigroup for type A. And think of, when you think about parametricity, we're not allowed to know anything about type A. There literally is no way to write this down. We can't even cheat and try to do some weird def that captures the semigroup ahead of time, whatever, because we have this type parameter A down to combine here. And because this combine method has this universal quantification here, there's nothing we can capture out, above this method such that we're going to have a semigroup for this value A. So we cannot provide this monoid for option, but we can provide a monoid for option. A lawful definition of semigroup K for option. And basically, it's this. Uh-oh. Oh, no. There we go. So basically, the definition of this is X or else Y. So it's sort of interesting that, and we could go through the associativity law and show that this holds. It does in fact hold. But basically, we can define a semigroup K for option that can generate an infinite number of semigroups for any old type, but we're going to have different behavior for that semigroup than we did for the more useful or expected semigroup that we used a couple weeks ago. Right, so to show you what I mean, if we did opt SGK dot combine and we passed like sum1 and sum2, we get sum1 as a result. If instead we just said the monoid for option dot combine sum1 with sum2, we're going to get 3 as a result. Whoops. Of course, that makes no sense. I asked for the monoid for option, but really I have to say option, a monoid for option int. We get sum3 as a result. Or semigroup I could have used. I didn't need monoid here. So anyway, that's an interesting case because for one type, option int, we have two different type class instances and they're both useful. Okay, let's do the same thing now with monoids. So remember, a monoid was defined taking a a proper type, and it extended semigroup and just added this empty operation. Well, so we can have MonoidK. So MonoidK is going to extend semigroup K. It's going to be defined taking a type constructor, and it'll just define an empty method that also is universally quantified. So you give us any old type parameter A, we'll give you back an empty f of A. Given that we just showed both a semigroup K for list and a semigroup K for monoid, to extend those, a semigroup K for option, to extend the list and option semigroup Ks to monoid Ks, we just need to define this empty operation. We can define an empty for list as just the empty list, and we can define an empty for option as just none. And there's like this neat correspondence when you think about it. We're saying that this ability to have an empty f of A for all A's, that has a correspondence to the notion that option, its none value extends option of nothing, right? I mean, it's going to be, maybe it's going to be hard to see at the REPL, but if you were to look up like the source code for none, you'd see it extends option of nothing. Option is defined covariantly in its only type parameter so that none ends up being a subtype of option X for all X. And nil works the same way with list, right? Nil extends list of nothing, and because list is defined covariantly, it ends up being a subtype for every list X for all X. And the correspondence there with like those subtypes, being like list of nothing, directly corresponds with this empty operational MonoidK. So we can sort of start to see where we're going in that like this empty operation is the key operation we need to implement filter. And I should point out, like MonoidK has the same laws as monoid. They're just all universally quantified. So in the same way that like Semigroup K use the same laws as semigroup, they just have to, those laws apply to every single type A you stick into these the combine operation. Same thing here. The monoid laws added like left and right identity, remember, to the operation. So like combining empty with a value gave us back a value. Combining a value with empty gave us back the value. MonoidK works the same way. It's just we can stick any old type in and it has to work. So we've defined two type classes, Semigroup K and MonoidK, and we really want now to be able to talk about a type class that has the ability of having this empty operation, but that also has the flat map operation and the pure operation that we were using. So we can just invent that type class, right? There's nothing magical about type classes. They're just, an interface to a family of types that share some common behaviors defined by laws. So we're going to invent a type class called MonadFilter. MonadFilter. Here's our MonadFilter type class. And MonadFilter, we're going to say extends monad, so we get flat map. And we're going to add our empty operation to it. You can see empty is universally quantified for all A, and we've got this f of A parameter being returned. And then we can define filter the way we did before, right? So filter is just flat mapping. If the value passed, in this case we're returning pure A, but we could also have returned FA. Actually, no, that's not true. It has to be pure A. And then otherwise, we're just using empty here. And then we're going to require some laws for the way empty interoperates with filter. The way empty interoperates with flat map. So let's look at MonadFilter laws. These are the two laws we're going to require. So you can see first we're going to start with all the monad laws. So we have like monad left identity, right? Like left identity and right identity of flat map and pure. We have the various laws we inherit from applicative. We have the various laws we inherit from functor. And we're going to add these two additional laws. Here we call it left distributivity and right distributivity. You could also think of these as like another type of identity law with the way empty and flat map relate to each other. So let's look at what they each mean. The first says that I'm going to start with an empty f of A, right? Because empty A gives us an f of A back. So I'm going to start with an empty f of A. And then I'm going to flat map over it some arbitrary function f. It doesn't matter what it is. This function can do anything in the world. And since we're just flat mapping, we're getting back now an f of b, right? We had an f of A, we flat mapped an a to f of b over it, so we get back an f of b. And we're going to require that the result of that must be equal to empty b. Now, empty b gives us an f of b, so type-wise they align. But when you think about it, this is a very strong property because f could be implemented as anything in the world, right? Anything that takes a value a and turns it into an f of b. We don't even know what b is. And yet we're going to require that what comes back is an empty b. So this is a very strong law. And it makes sense for things like none and for things like for an empty list, right? Because like flat mapping an empty list, what does the list flat map operation do, right? Well, it says, apply each element in the list with a function. That function is going to return us a new list, and we're going to concatenate all the results up. And so if you start with an empty list, I can flat map a function over an empty list. That's not actually going to have any values to apply. And hence I'm going to get back an empty list. And so this ends up being okay. None, the argument works the same way, but there's other types that maybe are more interesting in the way their empty is implemented. Okay, so that's our left distributivity. Our right distributivity law, we're going to just do it in reverse. Rather than having a function from a to fb, we're just going to take some random f of a. Give us any old value f of a. We're going to flat map on that and turn the a value into an empty. Right, so we're flat mapping, so we have like an a to f of b. In this case, we just happen to choose a as our output type. We wouldn't have to. We could change the type parameter there. But the important thing is that we're like completely ignoring this value itself and just turning it into empty. And we're going to require the result of that gives us back an empty value. And you can see, like, again, both none and nil adhere to this, right? Because if I have an empty list, if I take some random list of A's, like list 1, 2, 3, and I convert the value 1 into a nil, and concatenate that with the result of 2 into a nil, and concatenate that with the result of 3 into a nil, I get back a nil, right? 3 empty lists concatenated together is going to be an empty list. So they both trivially implement this. This is sort of even stronger limitation than just this one, though. Not everybody agrees that the MonadFilter type class should include this law. I'm not sure how I feel about it, but I haven't found any type classes that I want to write an instance. Sorry, I haven't found any type constructors for which I want to write a MonadFilter instance that don't adhere to this right distributivity law. So until we find such a one, I'm going to continue to require this to exist. Okay, so MonadFilter was the bare minimum that we needed to extend to a monad in order to give it this filter operation. And the reason this is better than where we started, just adding filter directly to monad, is because now we have these laws that let us reason about how empty and flat map affect each other. But we're not using SemigroupK or MonoidK here. And MonoidK has the same empty. So what if instead of defining empty as a member of this, what if we just define a new type class that merged together both a monad and a MonoidK? And we have that in the MonadCombine type class. It's hard to see in this definition because of some other type classes we're pulling in, which we'll also talk about in the future. But you can see we're pulling in MonadFilter. So anyway, we are a monad. We're also pulling in this type class called alternative, but alternative ends up pulling in MonoidK right here. We're not going to talk about alternative today, but we do have this MonoidK type class getting pulled in here. So a MonadCombine is really just a monad plus MonoidK. We could write it as such. Right, we could change this to just monadF with MonoidKF, and we get no different expressiveness. We get exactly the same expressiveness, the same functions, right? The same everything, the same laws, etc. It just so happens that we have in this library structures that we're working with, we have a lot of these other type classes like alternative, like monoid or MonadFilter, where we want them to all interoperate. We want to reduce, code duplication. We want, every MonadCombine instance to also be a MonadFilter instance, for example. So we define it this way instead. But really all we're saying is add monad and MonoidK together. We don't need to define an empty operation because we're getting empty from both MonadFilter and from MonoidK's empty. So that's interesting, right? Because MonoidK, the only laws that we required empty to adhere to were the generalized monoid laws. We had these two identity laws, left identity and right identity, that just said, like, when you combine an X and an empty, you get an X. And when you combine an empty and an X, you get an X. But as soon as we pull MonoidK into monad, we're going to define these MonadCombine laws. And the MonadCombine laws, we're only going to define one of them because we're going to pick up the others from MonadFilter. We'll start with those same left and right distributivity laws that we just looked at with the way empty interacts with flat map. But now we've got this extra combine. And like we've made empty now satisfy like two constraints. Empty is satisfying all the MonoidK laws, but it also has to satisfy all the MonadFilter laws. And now we need to define some behavior of the way the combine operation needs to work, right? We've constrained empty to those two things, to the the intersection of the constraints of those two, or the union of the constraints, the intersection of the behavior of those two type classes. But now we have to say how combine works in conjunction with flat map. And so the way we do that is this left distributivity law. And we're basically saying that flat map distributes over combine operations, or the combine operation distributes into flat map would be a way to say that. So basically what we're saying is that given two f of a's, here they're called fa and fa2, just given two random f of a's, we could either combine them together and then flat map some arbitrary function f, or we could distribute that flat map inside the combine operation, right, over the combine operation, where we're going to flat map f against the first fa, and we're going to flat map f against the second fa, and then combine the results. And so, like, if that feels like, you know, multiplication, it's a good intuition, right? Certainly, like, integer multiplication is distributive. We can say, like, we can say, you know, 1 plus 2 multiplied by 3 is, of course, 1 times 3 plus 2 times 3, right? And that very notion is what we're describing here. In this case, we happen to be talking about like a ring, like an algebraic ring, with the way like the multiplication operation interacts with the addition operation. Here we're talking about like a different type of ring, or at least a ring-like, algebra-like relationship with the way flat map is playing the role of multiplication and combine is playing the role of addition. Now you have to be careful with like reasoning like that because like I don't think these things actually form like an abstract algebra ring. So if you start taking other things you know about addition and trying to apply them to MonadCombine, you'll certainly get yourself into trouble very quickly. But you could take the definition of like you know, the normal ring defined on integers and promote it into category theory and then draw relationships between the way it behaves and the way some of these type classes behave. Okay, so we have MonadCombine. We have MonadFilter. We started here because we wanted something practical, right? We wanted to be able to filter on a monad. And we rejected the initial design of requiring like a monoid as an implicit parameter, because then that monoid could be any old empty. And we, when programming parametrically, we wanted to make sure the empty we got, you know, was lawful and had certain behaviors as it interacted with flatmap. We ended up in maybe a kind of a strange spot where we have something that's very general. We have this MonadCombine instance. But we don't really understand maybe why we're doing this. So I want to look at one derived method on MonadCombine that is very useful from a practical perspective. And that's this unite. And I think we looked at this one other time. Unite says that given an f of g of a, if f has a MonadCombine instance and g is foldable, we can turn it into an f of a. So I'm going to show an example before we look at the implementation. An example of this use shows up quite a bit. My Sublime stuff there's some weird bugs with the way the SVT plugin interacts with vintages. Okay, so let's say we've got this list. I'll call it X's. So here we have this list with sum 1, none, sum 2, sum 3. So clearly it's a list of option int. In previous weeks, we showed how we could sequence this list, for example. And remember, sequencing kind of inverted it. It turned a list option int into an option list of int. And we showed how, because sequencing relies on the applicative instance for option, the applicative instance for option is fail fast. So as soon as we hit a none, we got a none back overall. Well, sometimes we don't really want to do that. Instead, we might want to do like the equivalent of, you know, maybe something like X's collect. This is using the Scala Collections framework now, right? Let's collect any sum X and return that value X. And here with collect, we basically said, do a pattern match on the result. If it matched this sum x, then pull out that value. Do not return it as an option, just return it as the raw x, as the integer. And since we didn't have a pattern match case at all for none, that entry got filtered out. So this collect operation let us go from a list of option ints to a list of int with only the sums remaining. MonadCombine basically lets us abstract over this notion of collecting on collections. It happens to be called unite, but we could just say x's.unite. And you can see we get the same result, list 1, 2, 3. We didn't have to pattern match, though. And really, it's just requiring that our outer collection type be a MonadCombine instance and the inner type be a foldable instance. So let's look at how we implemented it. We started with a flat map. So we have an FG of A. We're going to flat map on FG of A, which is going to give us a GA. Now that we have a GA, here, in our example, G was option. So we have an option int at this point. We're going to fold map over that GA. And remember, fold map lets us convert each A into something that has a monoid. And it's going to accumulate all of the results of calling this function for each A into a monoid. So anyway, you can see here what we do. We start with GA. Now for each A, we're going to return something that has a monoid. Well, we don't have a monoid for A here, right? At least in this function. A is universally quantified here. We have no evidence that A has a monoid instance. But we can synthesize a monoid instance using MonoidK, right? Remember, MonoidK defined this toMonoid method. toMonoid just took some arbitrary A and gave us back a monoid for f of A. And so anyway, because we're in MonadCombine, we know that we've got this toMonoid. We can turn any A into a monoid f of A. Then what we want to return here is just an f of A. And so we return that f of A by lifting it into f. Right? So basically what we're doing is saying turn each g of A, or take each g of A, fold over it, and for each A inside of it, turn it into an f of A, and use the universally quantified monoid definition to combine each of those f of A's into a single f of A. So I think unite is a very interesting example because it comes from a very practical place in code when working with collections. You want to be able to do things like strip out all the nones and give you just the sum values. And yet it's bringing together a whole host of different type classes. Right? We're using monad, we're using MonoidK. And if you pull in all of the other parts of like the type hierarchy, we're getting things like semigroup monoid, semigroup K. We're getting things like functor and applicative. Almost everything we've talked about so far is getting pulled into this one example. And of course, this works with arbitrary type constructors, f and g, as long as the outer one is a MonadCombine and the inner one is a foldable. So as an example, let's just do an example where we invert the two type constructors. So we'll call this one wise, and we're going to say wise is equal to sum list 1, 2, 3. Actually, I want to do that a little bit different. We're going to say option list int. Okay, so wise is now an option list of int, and because list is foldable and option it has a MonadCombine, we can unite this as well, right? We can just say wise.unite. And we get back something much different. We get back sum1. Does anybody want to take a crack as to why, when we inverted the two parameters, it appears that we got the first entry from the inner list? What's happening here is that think about unite. What we're going to do is we're going to flat map on the FG of A. So we have an option list int. So now we're at, G of A here is going to be a list of integers. Now we're going to fold over those integers and call this little callback function here for each individual int, right? So we're going to wrap the number 1 into a sum, right? That's what pure here is going to give us an option back. So we're going to convert 1 into sum1, 2 into sum2, and 3 into sum3. And we're going to combine sum1 with sum2 using the monoid instance we get from MonoidK. Well, our outer type is option, so our f here is option, right? F is option. And hence, we're going to get the behavior of the behavior of this monoid here is going to be whatever the MonoidK type class instance does for option. And remember, we defined it at the REPL earlier, but here's its definition in our library here. The combine operation for option is implemented as or else. So it takes the first defined option. Well, since we're lifting every element of the list into sum, uniting an option list is always going to give us the first element of the inner list in the sum constructor. Right? Because like sum1 or else sum2 or else sum3, of course, we're going to get sum1, given this definition. We could define an alternate definition for options, an alternate MonadCombine type class instance that would also be lawful just by reversing the order. So let's pretend like this one is an alternate definition. I just called it combine prime. We could just say FB or else FA. This also passes the monad laws, right? We didn't change the order of our parameters. We're just evaluating them in the opposite order. And if we actually did the same example using a combined prime, that looked like this, we would actually get the last defined entry in our list rather than the first entry, right? Because we're going to say sum1 or else sum2. Oh, the answer is sum2. Now sum2 or else sum3. Oh, the answer is sum3. So just keep that in mind for a moment. I'm going to now wrap up today before questions by showing what these same type classes are called in Scala Z, because Scala Z does not use these same names. And while I think in the long term we might be using something other than Scala Z for functional programming in Scala, certainly at least for, let's say, the next 6 months to a year, we will be using Scala Z. And so I think it's important to give the roadmap here of what these names are in that library. So let's go take a look real quick. So let's go to Scala Z. The first is Semigroup K. That was one of our most basics, most basic type classes from today. In Scala Z, it's called Plus. There's a lot of stuff here. You can see that like Plus instances compose, right? So if you have like 2 Semigroup Ks, you can create a new Semigroup K. There's like this product type, which I don't really want to get into. But if you boil it down, you can see there's our combine operation, right? A universally quantified plus method takes an f of a and a lazy f of a and returns you an f of a. And here's the toSemigroup method, which just pushes the f constructor into the semigroup parameter. Okay, so plus is Semigroup K. The next one would be MonoidK, and in Scala Z, that's called plus empty. I should point out that like the names plus and plus empty come from Haskell. Specifically, they come from a package called semigroupoids in Haskell. It's Ed Kmet's category theory package. They're not like built into Haskell proper. They are an add-on package. And Edcomet certainly had a large influence on Scala Z, so hence the names here are from that library. But here you can see plus empty is just extending plus, and it adds the empty operation. Here's our two monoid operation down below. And again, you can compose these and you can create product types, but we're not going to get into that today. You can see like the documentation for plus empty is that it tells you it's a universally quantified monoid, which I think is a fun phrase, or it's it sounds certainly very impressive. Really what they're just saying there is that it can generate you a mono, it describes a type class F that can, it describes a type constructor F that can generate a monoid FA for all A. So the universally quantified, that's the idea that for all types A, we can give you this monoid FA. Okay, those are the first two. I'm going to jump to the last one we looked at was MonadCombine. In Scala Z, that's called Monad Plus. Monad Plus is also in Haskell. Haskell uses the same name, and this is actually in Haskell proper, defines Monad Plus, or I guess it's like the control package, well, nonetheless, it's proper Haskell that defines Monad Plus. Note the type, the base types here. We have monad, and we have this thing called Applicative Plus, which is really alternative. Structures and cats, we use this thing called alternative. Haskell actually also calls it alternative, but in Scala Z, they call it Applicative Plus. You might remember very briefly when I pulled up alternative, we saw that alternative extended both applicative and MonoidK. So same thing here. Their Applicative Plus extends both applicative and, in their case, plus empty. And so anyway, this Monad Plus ends up being the same definition of what we had. But what's more interesting is what's not here. What's not here is MonadFilter. And so Scala Z has no notion of MonadFilter. You don't need Monad Plus all of the time, right? Like a lot of the times, if you only want to do filtering, you don't need a full Monad Plus. You really just need an empty operation that behaves a certain way with respect to flat map. And so if you have some type constructor F such that you can define a empty method that behaves that way, but you can't define a combine operation that meets the semigroup laws, the Semigroup K laws, then you can't have a Monad Plus instance, and hence you can't filter on it. So what we've done in structures and cats is basically inserted that Monad filter type between Monad and Monad Plus as a way to capture more type class instances that support filtering. And there's actually some reform proposals in the Haskell world to do the same thing, to be able to talk about filtering without talking about full-on combining. In the Q&A, there's a question: where's empty coming from in Monad Plus? It's picking up empty from Applicative Plus, because Applicative Plus pulls in plus empty, so we get empty from here. There's one other interesting thing derived method-wise that we can do with Scala Z that we can't currently do with structures, and I don't think we can currently do with cats, and that's this separate. So I'm going to show a quick example of that, and then we're going to be done for the day. So let's look at separate while I get the REPL up and running. Rather than just having an FG of A, we're going to have an F of G where G takes two type parameters, G of A comma B. We're going to require that G is bifoldable, not just foldable. And we haven't talked about bifoldable type classes, but you can imagine it's an extension of foldable that works on type classes that take two type parameters, like a map, for instance, right? Map of key comma value is a type constructor that takes two type parameters. And so this is kind of neat because given a single f of GAB, we can turn it into a tuple of FA and FB. So for a very common example, something that you will run into a lot, we can do this. Let's import Scala Z. And here we're going to say val x's is a list. And then we're going to use disjunctions. So we're going to say, let's say 1.right, 2.right. We're going to say oh no's dot left, 3.right, and it crashed dot left. Okay. So we get here a list of either strings or integers. And now maybe like what we want to do is say, well, give us a list of all the good values out. We're going to go do something with those values. And give us a list of all the bad values out, all the left values out. We're going to log all those, or create some status items, or just somehow report on them. And x's.separate does exactly that. So x's.separate, you can see, has just filtered our list into the left values and the right values, but it got rid of that disjunction type constructor in so doing. So this is something that comes up all the time when working with disjunctions and lists. And if you don't know about separate, you've probably written code that does this logic directly. And so my final thought then is that just kind of talking about why we're doing these things, I think there are at least two levels of like engagement when we look at functional programming at this level. Sort of the first level of engagement is that you just want some nice, useful functions that get your job done quicker, right? You're dealing with like lists of strings or ints in your code, and you want to be able to do this separation. And rather than hoping that someone has provided like a method in the standard library to do whatever it is that you're trying to do, you can, assuming you've got a nice library like Scala Z, you can just get that code reuse in the form of things like separate. Maybe unlike sort of standard approaches at code reuse, or maybe not standard, but uh-oh, I think we lost the meeting. Is anybody still there? Are folks still there? Someone will write something in chat if they can hear anything. How about now? Can folks hear now? Hello, hello?
Yeah.
All right, sorry. VPN dropped, and that caused an issue. Yeah, so what I was saying is that sort of the first level engagement on using these libraries or using these type classes is purely one of convenience and code reuse. When working with some complicated types, maybe you've got like lists of disjunctions or whatever, you either are doomed to duplicating code all the time, like rewriting the same basic loops, rewriting the same basic algorithms, or you can get code reuse in the form of these type class libraries. I will argue that code reuse in the form of type hierarchies in the object-oriented sense is a failed experiment. And the Scala Collections library is a great example of such, where implementation details of their code reuse strategies are leaked all throughout that library. If you want to get scared, go to the list type and look at all your super types. Like actually use a tool to show you every super type of list, and realize that like there are more things there than we've even talked about so far. And that has nothing to do with principles, and has everything to do with them finding efficient ways to do code reuse. So while a lot of these ideas are foreign, while working with type classes are foreign when we're from a OO background, it lets you work with code reuse or get code reuse and take advantage of code reuse in a much more simple way than something like standard OO techniques. And then the deeper meaning here, the deeper engagement here is that the one of parametricity, which we talked about last week, the one of being able to write generic codes such that you can't accidentally take advantage of some piece of data you weren't supposed to take advantage of. And I think that's something that comes with time. So so absolutely, like, start using this stuff in the sense of like, I want to, I've got this list here of disjunctions and I need to split it apart. Well, I remember that Monad Plus thing gave us this separate operation. That's a great way to start. But keep an eye towards this notion of parametricity and being able to reason about these abstract types. So that's all I have for today. Is there any questions? All right. Well, I know everybody's got stuff at 2, so thanks for coming.